All right, so let's get started. So the same as previous, we'll go through several Q&A. So the first one is like folks are asking about like caches for bypassing patch cache, because I think the point is like using patch cache, we can accelerate the time to get a file from a storage device. Because if the file are cached in the patch cache, then the application doesn't really need to read them from a storage device. But there are several cases that the the application designers will avoid using patch cache. So first one is called direct IO. So direct IO usually like using some database, because for some like large application like database or like some machine learning application, those kind of stuff, they can have their own user buffer. In that case, using patch cache will not really benefit, because like if you open the patch cache, then for each of the file requests, you need to get the data from patch cache. And in that case, if you are an user process, then you need to interact with the operating system very frequent. So in this case, if the application, for example, it can say, I want to get a super large memory, and the application can manage the memory by itself. In that case, it doesn't really need patch cache. So the application can directly use a direct IO to get the data from the storage device. And the second one is the synchronous IO. So the idea behind synchronous IO is because the consistency issue. Like if we use a patch cache, and if in some cases, for example, the power shortage or like the operating system crash or like the system crash, then there are a very low probability the cases the data doesn't really sync with the storage device, because if you write the data, in most cases, if you have patch cache, the write operations will first modify the data in the patch cache, but will not directly modify the data in the storage device at that moment. So using synchronous IO, you can update the data both in the patch cache and the storage device. But in that case, you doesn't really take the advantage of the patch cache. Okay. But the good thing is you can make sure 100% of consistency. No matter the system crash at any time, you don't really need to care about the consistency, because every time you update the data back to the storage device. Okay. So the second one is about NAND flash SSD. Like someone is asking about like, actually there are several issues NAND flash SSD will face, like write amplification and like lifetime issue. And actually the SSD controller inside the SSD can take care of. And there are some special cases. For example, some cases like operating system can help. For example, currently there is a command named the trim command from operating system. And the trim command is, the main idea behind the trim command is to send the hint. For example, if a user delete some files, then the trim command can send those information to the SSD controller. But without this operating system support, SSD controller can still take care of also like all of the challenges in SSD. And this is why we need SSD controller. So we don't really need the operating system support or like even the application support, and SSD can do the things by itself. And this idea is also same for the SMR, because like SMR needs to do the sequential write operations. So it will also face the challenge that SSD face, just like garbage collection stuff. And actually, operating system doesn't really know you are using SMR or hard disk drive in most cases. So operating system will not really customize a garbage collection for the SMR. And in this case, SMR should have their own controller to run the garbage collection. Okay. So usually most of the storage device, if they have their spatial constraints, in most cases, they will have their own firmware to deal with this kind of constraints. Doesn't really need to bother the operating system. Okay, So I think there is a very interesting question is about as hard disk drive density increase. I mean, because if it is possible to reduce the track wide, then you can increase the density of hard disk drive, right? So in this case, read head will face several issues because for each track, if it becomes narrow, then the read head will face the weaker magnetic signal interference, and mechanical precision is hard to be controlled. So it does increase the challenge for read head. But I think for current manufacturing technologies and HDD technologies, most of these issues can still be handled. Okay. So the last one would be the QLC compared with the MLC and SLC NAND. Because let's first do some record, like using QLC or like using MLC, it means like in the same cells, you are going to decide 3 bits or even 4 bits. So for 3 bits, it means you need to decide for 2 to the 3, like add labels. And 4 bits means you need to decide for 16 labels inside one cell. So the things will be like this kind of stuff. Like right after programming, you will get like 4 possibilities for the 2 bit cells MLC. So because using almost the same voltage value, like from 0 to VT, actually you need to decide more labels here. So it does increase the challenge for the how to precisely control the voltage, and like if there's error, then how to deal with it. The error occurs because like look at the figure again. If there are some retention errors, then probably each of the package here will become loosey. I mean, loosey is this is a tight and this is a loose. The red one is a loose. So loose means like because there are some error, so it looks like this. And then for 1, 0, 0, 1, and 0, 0, you can see in a picture like there are some portion of the possibility it will cross the reference voltage. So for this area, and this area will be misjudged. For example, if the data if the voltage in this area and we read, it is possible to read the data inside the cell, then it will be judged as 0, 1, for example. But actually here for this kind of cells, actually there are 0, 0, not 0, 1. So there is a misjudge here. And this is the reason we say for MLC or even QLC, because there are more cells, so even very few retention loads, it will make the read process becomes harder to read out the data. Okay. So this is about the narrow margin issues here. Okay. But actually, we did not cover this so deep in this class. So if you're interested in, we will have a class talking about this kind of stuff in the next semester. Okay, and the other thing is about the hard disk drive part. So last week, some of you are asking about the zombie recording. So I just moved the slides for from the next semester to here. So this is our plate, right? This is one plate, and on the plate there are several sectors. So the number means the sector ID, and this is the outest track, and this is the innerst track. So you can see the size for the sector on the outest track is quite, I mean, will be like 2 times or even 3 times larger than the sector in the inner track. Okay, but in general, I mean, if we don't use a zombie recording, in general, they are all 512 byte. So I mean, like for this sector, even it has larger space, larger area in the physical perspective, but it can only store like 512 byte. So it wastes some of the physical capacity here. So a better way is about to store more data on the outer track. So like this, actually, if compared with the size, actually this size would be very close to this size. So actually for the outest track, actually for this region, we can store like three sectors in this outer track. Okay, so it means like for the data density, we can store like in this example is 3 times more data in the outer track compared with the inner track. Okay, and then the throughput will definitely increase because actually the spindle like here and it's swiped from the left hand side to the right hand side. So for a time unit, actually it can read out more data compared with the inner track. Okay, so using the zone B recording, it does increase the throughput of the SSD. But actually there are okay. So the reason like it calls zone B recording is because in this example, like the middle circle means the traditional one. So this is the disk track, and for each track there are sectors on it. But if we are going to use zone B recording, then we will partition the tracks into several zones. So the outer zones means like we will increase the density of the track. For example, outer zone means we can store more the data in the outer zone, and the inner zone, like you can only store fewer data inside. So there are some here, like for zone 0, then there are 15 sectors per track. But if you are in the zone 6, then you only have 6 sectors per track. Okay, so one zone is possible to include like 2 or even 3 tracks inside. And this is all good things for a zone B recording, but there are also bad things. Bad thing is about like if we're going to use a zone B recording and when we are going to do the address mapping here, and the issue will be you need different address mapping, or like even you need some extra, I would say like insignificant extra space to record about, okay, so which tracks are in zone like zone 0 and which tracks are in zone 1. Okay, but if you are using a traditional one, you lose the high throughput, but you don't need to have this kind of complex addressing here, because for each track, the number of the sectors on it will be the same. Okay, so this is about the zone B recording stuff. Okay, so let's first do some recalls on the hard disk drive and solid state drives, and we still have one slide left for the SSD. Okay, so for the hard disk drive, the same example, like this is our plate, and there are several sectors on it. So actually, the disk performance, there are 3 main factors here. The first one is seek time. So seek time is about the distance to move the read head from like this, from the inner to the outer, or outer to the inner. This is about seek times. So because seek times involves the disk moving, so disk movement is a mechanical moving, so it takes slightly long time, like 4.9 milliseconds here. And then rotation is about the time to rotate the plate. Okay, so the rotation, like if you're going to buy an hard disk drive, then you will see like there's called RPM stuff, and you can calculate how fast it is for each run. And the third one is a transfer time. So transfer time is to rewrite data to the surface. Okay, so use the GMR to read the data, or like to use the write head to write the data. It takes sometimes. Okay. Okay, so we also talk about the random access and sequential access. The key thing is about for the seek times, like if you're going to frequently move from inner to outer, outer to inner, it takes time. And also, if the data is not aligned with the rotation directions, then it also takes time. So sequential access also always has a good performance for the hard disk drive. But if it is random, then it takes longer time. And actually, I also read a question is about like, is it possible to control a random, or like to control the access pattern? And in most cases, access patterns are decided by the user or applications. So it is not easy to say like if this is, for example, a random access, and in the systems, I mean in the OS systems or in the hard disk drive, we try to make the random access become sequential. It is hard. But I mean, if there are some like power cache inside, and then if you are going to do some scheduling, then maybe it is possible, but not for all the cases. Okay. So also, like we talk about how to really read and write the data from the hard disk drive. So this is a track, and on the track there are several sectors. Okay, so in the sectors, actually, there is a things called recording medium. So each recording medium you can think about is called 1 bit. Then each head, I mean each hard disk drive head, it comprises the read head and the write head. So read head is using the technology called GMR, and write head is inductive write. So the size of the head is different. It differs a lot. So how to store the data? Then first, how to access the data? So read head works like this kind of stuff. So image, this is the recorded medium, and this is our read head. And this read head comprises a free layer and a fixed layer. So actually, when we are going to read the data, it depends on the directions between the fixed layer and the recording medium. Because fixed layer is fixed layer, so the direction is static. And the recording medium depends on what kind of data you're going to store inside. Is it 1 or 0? Okay. So using GMR, when GMR kind of moved around this recorded medium, okay, then this recorded medium, because it already has the magnetic field inside. For example, in this example, the right-hand side is north and the left-hand side is south. So the magnetic field is from south to north inside this recorded medium, right? Okay, so when the GMR kind of moved across this recorded medium, then the magnetic field will sense the free layer. So the free layer will be sensed, and then the free layer will show these directions from the left-hand side is north, right-hand side is south. So actually, how to decide like what is the directions of the recording medium? Actually, it depends on the resistance value of the GMR, because when a GMR moves through the recording medium, the free layer is polarized by the magnetic field, and then we now fixed layer and free layer, they have their own magnetic directions, and in this case, they are anti-parallel. So anti-parallel will let the GMR shows higher resistance stat. Okay, so this is the characteristics behind the GMR. If the fixed layer and free layer, they show anti-parallel magnetic directions, then the resistance value will become high. So on the other hand, the fixed layer, again, is the same directions. And if now the recording medium now store the data like from the left-hand side is north and the right-hand side is south. So again, for the GMR move through this recorded medium, the free layer will be sensed. And this time is right-hand side is north, left-hand side is south. So in this example, on the right-hand side, the fixed layer and free layer, their magnetic fields is in the same directions, and we call them the parallel. So this parallel magnetic field will make the GMR becomes in the low resistance state. Okay, so actually the GMR will always, I mean, the hard disk drive will always give the voltage value to for the GMR, and then you have the voltage and you have the resistance, so you can get a current value. So sensing the current value, we can know now GMR is in a high resistance or low resistance. And if in a high resistance, it means this recording medium is 0. And on the other hand, if the GMR is low resistance, it means like it is 1 now. Okay, so a simple way to know how it is a high resistance or low resistance, you can just directly decide about like if the recording medium and the fixed layer, they are in the parallel directions, then it will become 0. And if the fixed layer and the recording medium, they are in the anti-parallel directions, it will become 1. Okay, so this is about how to read out the data by using this magnetic field stuff. And the right hand is using the inductive write. I think you guys already know this in your like junior high or senior high school. So it is about given the electron, and when the electron moves through the wire here, then there is a magnetic field. So the magnetic field can change the magnetic field on the recorded medium. And this is a reason why we need a larger write head, because the how strong the magnetic field is depends on the size of the magnet itself, right? Larger magnet, then you can get the larger force. Larger force can override the magnetic field on the recorded medium here. Okay. So this is about how to read out the data. and write data on the hard disk drive. And then let's move on to the solid state drive. Okay, so solid state drive, we introduce several stuff. One is about we break down the SSD. So given this is an SSD, so inside the SSD there are several components. First one would be there are several controllers inside. Okay, there are all microcontrollers, but there's usually not only one. There are several controllers here. So controller will take care of several stuff. We will give you an overview later. And in addition to controller, there are also a couple of DRAM on the SSD, and we'll tell you the reason why later. Okay, so actually next week we focus a lot about the right-hand side stuff, just like the NAND flash cells. So for the controller, actually it will connect with several channels. So each channel will connect with one chip. So one chip, there are several dies on it. So in this example, there are 4 dies on it. So actually, die will be the minimum granularity to get the request. So for example, if you have a read-write request and then you send into the chip, actually you can send up to 4 requests. They can be run concurrently. But if you send like add requests to one chip with 4 dies, then there are only always 4 they can run in parallel, and the other 4 they'll be pending. So until one die finish their request, then the die can use to serve for the 5th one or like the 6th one. Okay. So inside the die, there are 2 planes. And then for each plane, actually there are 1024 blocks inside. And the block is the minimum granularity to do the erase operations. Okay. So inside each block, there are 512 pages. Okay. So pages is a page is the minimum granularity for read and write the SSD. Okay. And then this is the details about what is the circuit looks like inside the block. So actually, for each of this, it is a memory cell. And last week, we focused a lot of time on introducing the how to read, write, and memory cell like this. Okay. So what is a page? Sorry. So a page is about like a lot of memory cells that chain by the word line. So here you can think about, usually we say for SSD, the page size is like 4 kilobyte. So it means like we will have 2,000 or 4,000 of memory cells that chain by the word line. So it depends on it is SOC or MLC. Okay, so this is a patch. And this patch is not, it's totally different from the OS patch. So they have no relation for these 2 stuff. Okay, so several word line they combine together, we'll call them a block. So this area is a block. Okay, so next, do some recalls on how to read, write, and the nameplate cells. Because I think last time I do a little bit too fast, so there are several questions after the class. So let me clarify now. So actually, this is a cell. This is one SSD cell. So the data is stored in the floating gate, and the form for data is about the electron inside the floating gate, and the electron will show different voltage value. Okay, so like high voltage value means like bit 0, and low voltage value like bit 1, like this kind of stuff. And like the bottom part is a P substrate. And then between the floating gate and P substrate, there is a dielectric layer. So dielectric layer works like an electrical insulator. Okay, so this one will be a wire and penetrate through the N source and N drain. Okay, and here will be another like wire here. And here is a control gate. So, sorry. So this memory cells, actually we rotate minus 90 degrees to this one. So actually, this is a word line, this is a bit line. And in this example, this is the word line, and this, the horizontal is a bit line. Okay, so how to do the program? How to write the electrons into the floating gate? Actually, we will apply a higher voltage called 20 volt. And actually, how much voltage it is, it depends on different SSD. And this 20 volt is just for an example here. Different SSD, different NAND flash, they will have different configurations, so the voltage will be different. So the only thing the same will be, if we are going to program, if we are going to write something in the floating gate, we need to apply for a large voltage on the board line. So we use 20 volt to apply on the control gate, and then we will give the 0 volt for the P substrate. Okay, so 20 volt is a high voltage, so it will make the electron inside the P substrate becomes delocalized electrons. They will become so excited, and because 20 volt give very enough of the energy to let this electron to cross through the dielectric layer. So this is an insulator, but if the voltage you give is enough, then the electron can jump into the floating gate. Okay, so this is about how to program it. Okay, and then how to read the data. Actually, we will use a lower voltage value also apply on the board line. And in this example, we use 2 volt. Okay, when you're using a 2 volt, actually in this example, because you use a lower voltage, so you can only make fewer electron on P substrate becomes excited. So in this example, you can only get 4 delocalized electrons in this example. Okay, but the thing is about 2 volt is not able to let this electron cross through the dielectric layer because the energy is not enough to make them become so excited to cross through the insulator. So it is not possible for those delocalized electrons to cross through the black one, the insulator. And then they will be captured from the end source and end drain. Okay, but the case is about because 2, in this example, 2 is too few for those electrons to create a current. Because for a current, it is more enough of the electrons to generate the flow. Okay, so 2 is not enough. So actually there will be no current to pass through here. Okay, so 2 is not enough. Okay, so here's no current. Okay, so the idea is about there's not have enough electrons, so we cannot read, sorry. So using the 2 volt, we cannot get the current at the end of this bit line. Okay, but there's another scenario. So the scenario is like this. We give the same voltage value called 2 volt here. Okay, but actually this cell doesn't be programmed before. Okay, so when you use 2 volt, you can make a little bit fewer more electrons to be excited. So actually even they are using the same 2 volt, but on the right hand side, because there is no electrons in the floating gate. So it means it doesn't, I mean, it means like the NAND flash controller doesn't program this cell before. Okay, so there are more electrons will become excited, and this delocalized kind of electrons, once again, they cannot jump into the floating gate because the 2 volt is not high enough to make them, to give them enough of energy to cross through the insulator. So they are once again be captured by the end source and drain. But this time, because they have more enough of currents, more enough of electrons be captured in end source and end drain, so it can generate a current. So from here to here. Then if you have a sensor at the end of the bit line, you can get a current. So with this current value, you can know, okay, so there is no electron inside the floating gate. But on the left-hand side, you cannot get a current. So you will know actually there is electron inside the floating gate. So with current, with electron, without electron inside the floating gate, you can define, okay, this one probably will be like bit 0, and this one like bit 1, like this kind of stuff. Okay, so the key idea behind this kind of reading stuff is because higher voltage value induce more electrons from the P substrate. And the number of excited electron is correlated to the voltage value. So if you use 20 volt, then P substrate will give you a lot, quite more. But if you use 2, then you can get very few. Okay, so we also give you an example for how to read out one patch, because in this example, there's only one bit cell. Maybe you're thinking about this is not realistic enough. So the example is like this. So one word line, we can have several memory cells on it. And in this example, let me just put 4 here. Okay. So patch 1, patch 2, patch 3, and patch 4. So for each cell, they have their own voltage value in their floating gate. Okay. So if now in this case, we are going to program patch 2. So actually, let's image like now for patch 2, we have 4 cells and they're all 1111. And we are going to program them to 1100. Okay, so this is from the user perspective, but actually from a circuit perspective or from an SSD perspective, actually in patch 2, actually it's about there are like 1.9 volt, those kind of stuff, because it is low voltage. Okay, so they're 1111. So if we are going to make this voltage change to 1100, then we are going to do this kind of stuff. We apply a strong voltage, 20 volt here, and then because we use 20 volt, so basically we will change all the voltage value for the four memory cells for patch 2, right? But actually we only want to program the last 2 cells, and the first 2 we want to make it the same. So the case is about we apply a voltage called inhibition voltage. So for this inhibition voltage, we can avoid this for the first 2 cells be programmed. Okay, so the idea is like this. Now the same things, we use 20 volt, and there are a lot of electrons becomes excited. And if there is no inhibitions, then those electrons will cross the accelerator. But because here is another outer force from the horizontal directions, so those electrons, before crossing the accelerator, they will be forced to move out from the engine, because here is another force, like 5 volt force, will make them hard to cross the accelerator. Okay, so this V INH V inhibition is here. We apply on the bit line, so we can avoid those cells. They are not going to be programmed. Okay, so in this case, actually we only program the last 2 cells. Okay, so their voltage value increased to 3.1 and 2.9 because there are more electrons inside this floating gate. Okay, so this is about the program. And the case is about, so how about how to read out the data from one patch. So the same thing, if we are going to read out the patch 2, then we will apply a relative low voltage. So in this case, we apply the 2.5 voltage here. So we apply 2.5, and then the thing is about, remember, if there's no electron inside, then if we use a 2.5 volt, then there are several more delocalized electrons. They will be captured on the end source and end drain. So it is possible to generate current. On the other hand, if there are already electrons inside the floating gate and you use the same 2.5 volt, you cannot generate a good amount of the electrons to create the current. So there are very few delocalized electrons becomes excited. So end source and end drain, they don't have enough electron, so it cannot cause the current. So the thing is like this. We'll have a sense, a read like the current sensing unit here at the end of each bit line. So for this sensing unit, for the first 2 bit line, we can get the current because if bypass it, we can get a current. But for this 2, actually, we cannot get it because there is no current value here. Okay, so in this case, the current value will be quite low. So for the patch 2, what we can know is the first 2 is bypassed, and the last 2, there's no current here. Okay, so it's 1100. Okay. Okay, so erase granularity. Actually, we need to erase in the block granularity. And okay, so the reason is just about because for the P substrate, okay, here, for a P substrate, actually on one P substrate, there are a lot of memory cells on it. So one P substrate, it accommodates a block of the flash patch. So P substrate, when we are going to apply a strong voltage to do the erase, actually a block of the NAND flash cells on this P substrate will be affected. So this is the reason like why erase should be aligned with the block. Okay, but the thing is like this. if the erase size is larger than the write size, then we need to do the sequential write constraint. The reason is now we program the data from low voltage to high voltage write. Then if we are going to program this high voltage data back to the low voltage state, then the thing we are going to do is called erase. It is to move the electron from the floating gate out of the floating gate, right? So each time we are going to update the data, it means we are going to do the erase. But erase unit is larger than write unit. So we will not really erase the data in place or in this place. We will write it to the other place, okay? So this is an example. So if we have this kind of NAND flash patch program to this kind of bit stream, then if we are going to update the data in those bit streams, actually we cannot erase this patch, because if we erase this patch, it means we are going to erase the whole block. But we only want to update this patch and we don't want to update the other patches. So a better way is to copy out this patch and then write the data in a DRAM or somewhere else, not in this block. Then write back to the SSD to another like patch, another new patch. They are not programmed before. Okay, so this is called remodify write. You read it, modify it in some other place, and write to a new flash patch. So in this case, we don't really need to erase the block. Okay. Okay, so this is about the remodify write. And then multi-level cells, I think we can just skip it. Just like you are going to represent more kind of bits in one floating gate. So you need a better way to differentiate different labels here. Okay, so QLC just mean like you are going to decide like 2 to the 3 bits. Oh, sorry, this is MLC. MLC is 2 to the 3 bits. So triple level cell, so you need to represent 3 bits, and QLC is 4 bits, so you need to have 2 to the 4. Okay, so let's move on to the SSD architecture here. So we talk about a lot here, NAND flash cells. Okay, but actually in SSD, like Phison or like Silicon Motion, in most cases, they focus on designing a controller, because there are several power constraints in NAND flash chips. So they're going to use some like firmware level solution to solve these NAND flash chips. Okay, noting that actually they solve this NAND flash chip issue inside the SSD, because this is an SSD, and outside SSD here is device driver. This is part of kernel, but most of solutions will be inside the SSD. So this FTO, you can think about, this is a firmware inside the controller, okay, inside the SSD, and the controller around the firmware. Okay, so there are 2 main blocks. One is called flash translation layer, and the other is called memory technology device, or MTD. Okay, so the first and the critical thing is about the sequential write constraint. So actually, SSD solves the sequential write constraint by using the address remapping. So SSD also uses same concept of the like virtual memory stuff. Okay, so there are virtual memory, you can think about like logical block address to physical block address stuff. So let me give you an example. If this is a NAND flash block, so block 1, and then there are several patches inside. So this is one patch, and the logical block address is called 500, and the physical block address is called 800. As you already know about like virtual and physical, is about virtual address is what user program or like what kind of application can know. So this one is a virtual logical block address. A virtual is for the like users or applications, and the real address or the physical address on the SSD is called physical block address, and both can be different. So LBA 500 can be mapped to PBA 800. Okay, so now we are going to update LBA 500. Okay, so a better way is, as we say, remodify write, right? We read out this LBA 500 patch and we modify in some place, maybe in this DRAM, like translation table here. There's a data buffer, so we modify in the data buffer, and then we write back to the NAND flash chips. So we modify, and then we write back to another block. So because this block, the latest one is here, so this patch, before writing this patch, it is empty. So we can write the new data to this patch. It doesn't really need to do any erase. Okay, but the case is about actually this one to this one. This one is PBA 800, and maybe this one is PBA like 1201, like here 1201. So if we are going to let if we don't want to let the user to know this kind of stuff, for example, we don't want to let the application know the constraint to aware of the constraint inside the SSD. Then a better way is we don't change the LBA. I mean, for the applications, for the user, they still use the same LBA. But the difference is about PBA. We remap the PBA from 800 to 1201. Okay, and the case is about if we are going to do this kind of remapping things, we need something like patch table, right? But this is SSD, so we are not using patch table. What we are going to use is about the things called SSD translation table. So actually inside the SSD, inside the DRAM of the SSD, there is also a place to put the translation table here. So this translation table will keep track of the mapping between each LBA and PBA. So with this design, actually, for the application, for the operating system, actually, they don't really know what is the constraint inside the SSD. Okay, they even will feel like maybe SSD just like hard disk drive. They can support like the ePlace update. Okay, and this is all because SSD FTO controller helps to cover all this stuff inside the SSD. So no one knows. I mean, no applications know what's going on inside the SSD. But the only things they are going to know is actually they can use the same LBA to do any stuff. They can directly update this LBA, and they can still get the right data because the SSD FTO will focus on help to remapping this kind of pageant stuff. Okay, and actually, this stuff will have another good thing is about, as we say, like we move the data from this patch to this patch, and the prior patch actually we will not erase it directly, right? Because if we are going to erase this patch, we are going to erase this whole block. So inside the FTO will mark this patch as an invalid patch. So there's just a big change inside the table. So maybe in the table, we will say like, hey, actually this patch will be an invalid patch. There's only a big change here. But the problem will be, if there are a lot of this kind of embedded patches inside the SSD, then we are going to do the garbage collection. Otherwise, we don't have enough space to store more new data, right? So when we are going to do the garbage collections, the same things, we need to erase the data. But for example, if we're going to do the garbage collection on this block, and this patch is still valid, but the rest of them, for example, they're all invalid. And before doing the erase, we still need to move the NAND flash patch to other place. So this will also need the address remapping. So running garbage collection inside the FTO will help to maintain the mapping table. So for the application, actually, they don't really know the SSD is doing a garbage collection or not. Because all those kind of stuff, they are covered by the FTO. And FTO will not really notify our operating system or application to say, hey, I'm not doing a garbage collection. No, FTO will just do the garbage collection at the time that FTO feels like it is time to do the garbage collection. Okay, so this is a good stuff because you just plug in the SSD, you just insert the SSD in your server, in your PC, in your notebook, and the operating system doesn't really need to do any change. Even your application, you don't really need to know what is the constraint inside the SSD, and the controller will help to handle most of the cases. Okay. 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 So the agent translator will update the translation table, and then we'll get the data from NAND flash patches again. Okay. So to get the data from NAND flash patches, actually we need this kind of memory technology device, so MTD. And you can think about MTD just about to get the data from NAND flash chips. So the FTO will ask the MTD to know about how to get the data, maybe what's the protocol of the read and write. So MTT will control this kind of data reading and writing things. And the other, the address translation, garbage collections, or even the wheel leveling, we can use, they are all handled by the FTO. Okay, so because we don't have more time to talk about the SSD in detail, so we'll have another course in the next semester, but I can give you some brief idea about, as we point out, like each patch, I mean, has their own kind of lifetime, because SSD cells will be worn out if the electric layer becomes so thin. And one day, if it is not possible to lock the electrons inside the working gate, then these cells will be dead. So when these cells becomes a bad cells, then if there are, sorry, one more patches here. Okay, here. So if there are too many cells in this patch becomes a dead cells or like a bad cells, then this patch cannot be used, right? So a better way is, let's make all the patches, all the cells be worn out at very close time. Like, for example, if all the cells, we can only write like 10 times, then we don't want to that a few of them reach the 10 times, but the rest of them only write like 1 or 2 times, right? So the where labeling is going to label the where. The label means we are going to distribute all the wheres to all the cells. So what we are going to do is to do our best to make all the cells to use up to like 9 times and or even 10 writes. So all the cells will be worn out nearly at the same time. And this is what wheel leveling is going to do. Okay, so actually wheel leveling is also controlled by the FTO in the controller. The FTO will say when we can do the wheel leveling, and wheel leveling actually is a combination of a lot of garbage collections. Okay, so garbage collection and wheel leveling, usually they will be combined together to do. Okay, so this is about SSD. Okay, so question? Okay, so next on, we'll talk about the block device driver. Okay, so the main idea behind the block device driver is, as you see now, you have hard disk drive and there's SSD. And hard disk drive and SSD, they show different characteristics. Okay, but if you are a user, you don't want to know you are not using hard disk drive or SSD, right? Because if you are going to make sure, okay, there are different kind of SSD, there are NVMe SSD, PCI SSD, and also hard disk drive, there are hard disk drive, there are SMR drive, there are also a lot of different drives, and you are going to give them different kind of management there. Okay, so you will be super tedious to do this kind of management. So a better way is about, let's do a abstraction, let's do a virtualize there. So user doesn't really need to know what kind of device you are now accessing to. We don't really need to know what is the characteristic inside SSD, the hard disk drive. So block device driver is a layer that doing this kind of device virtualized things. Okay. Okay. So maybe we can like cover 10 and then come back later.